let's look at some ways in which design of experiments fits into this strategy. And I'm going to show some designs, and I'm just going to show them in 3 dimensions. In other words, as if we're talking about 3 factors, because it makes the illustration easy. And also, we used to work in 4 or 5 dimensions, but we lost so many graduate students that way that we've decided to stick to 3 now. So now, when we start with a design, for example, like this, then what this design is a fractional factorial design. In fact, it's a design in which only half of that cube is being run, as you can see there. Suppose we started with that design. Now, there's any number of ways that we might decide to go from that initial design. Suppose we found in that design that there was a trend across the design. We can analyze those points and we can look for a trend. If there's a trend across in a particular direction, we might say, well, you know, what we're looking for is a high value of this thing, and there's a trend going this way, so let's go that way and go to this new location and do some experiments over there. Or similarly, if the problem was to reduce variation, there might be a trend in variation, and you can say smaller variation is in that direction, and you take off in that direction. So that's one thing that initial experiment might suggest to you. But going back to that initial experiment again, it might not be that when you did an analysis of that you found a very strong trend. And it might be there wasn't anything like that there, and you decided, well, this is a fractional design, let's run the other part of the fraction and make this a complete factorial. I put a couple of points in the center because those points in the center are very often useful for checking overall curvature. Another thing you might do, you start off with your initial design, and you might say, well, somebody might say, well, you know, this factor going this way is temperature. And you're saying you're not finding any effect due to temperature? That's strange. I don't think we're changing that over a sufficiently wide range. So let's widen the range of that. So rescaling the design is another thing you might do. Another thing we can do is to drop and add factors. Like here you see speed, temperature, and gate size. Well, you might decide that gate size isn't really doing anything, and so, but you're still interested in speed and temperature. You'd like some more information about that. So in a second design, you might still include speed and temperature, but switch gate size to, say, mix rate. And another thing you can do is to replicate some of the points, repeat some of the points. One reason you might want to do that is because sometimes you think you know how big the experimental area is, and then you begin to wonder. Sometimes people are unduly optimistic. They say, well, we've run experiments like this before, and the experimental area is only 2% or something. And when you start to get some very funny looking results, you begin to wonder, well, maybe they're wrong about that. So you'd like to replicate some of the points. And you notice there we've not replicated all of them, we've just repeated certain ones. Actually, we've replicated one of the half fractions there. Another thing you might want to do is augment the design. Now, what we've done in this case is, suppose it looks as if you've got large two-factor interactions, and this is representing twist in the surface with those interactions. After you've done this first analysis, you find you've got large from that first design, and what you really need to do then is to look for the curvatures also, and to look at curvatures. If you're going to run a factorial design, you'll have to run 3 levels of everything. That'll involve you in some largish number of runs. Better way to go is to add these points around the design in the way that's shown there, and you can augment the design, and from that you can look at the curvatures and the interactions and conclude what the general shape of that curved surface is like. Now, remember that when we started with that first design, I'm just saying all those things could have come out of that first design. Depending what we saw, we could do a whole lot of different things. And so we're adapting our design strategy to the way that an experimenter normally works. We're not putting shackles on him and saying, you've got to stay with this statistics thing is not going to let you be an experimenter anymore. It's going to put you in some shackles, and the real guy who's been running things as the statistician, it's not going to be like that at all. This is a technique he can use himself and fit into his normal way of going about experimentation. So I want to talk about some other aspects too of this philosophy. Sometimes people say that if you're running experiments on a process, it could be a process manufacturing something, or it could be a process of, say, analytical process, chemical analysis or something like that. Sometimes you hear people say, first get the process in a state of statistical control, then you can run experiments. Well, the problem with that is, I mean, I agree that you should try to do that, and you should try to get everything under as good a control as you can when you're going to run experiments. But sometimes if you were to insist on having everything in perfect control before you ran any experiments, you just never run any experiments, because some of the problems you're running into, you're going to find out by running experiments. And actually Fisher did not, when he invented the design of experiments, did not make the assumption that everything's in a state of control. And certainly the agricultural land that he was experimenting with wasn't in a state of statistical control. If you look at successive plots across a field, it's not a fixed mean plus random variation about that mean. A sheep died over there 10 years ago, and that bit over there is a bit more fertile. There's a lot of stones over there that was once a river going through. So you get this kind of thing happening. And what Fisher did was to solve the problem of how to run experiments when the system is not, the underlying disturbance is not in a state of statistical control. The way he did it was to say, let's split up the experimental material into small blocks like that. And you can see if he wants to compare 4 treatments, say, B, A, C, and D, A, D, B, and C, he runs those in random order within each of the blocks, and you can draw valid conclusions from that. So randomization and blocking is an important idea. Another thing that you have to think about very carefully is the choice of the objective. And the choice of the objective must relate to the true aim of the investigation. I already mentioned the case where I said about computer chips, you wanted to increase the yield of computer chips. Well, that's what you thought you wanted to do, but not at such an expense that it would cost you actually more to use the modified process in the end than it would to go on doing what you're doing already. The choice of the objective must also be understandable. Sometimes, for example, when I've worked with experimenters, I've liked to have at least 2 people there, because if you have 2 people there and you say, well, what are we trying to do in this investigation? Well, if there's 2 people there, the first guy says, well, what we want, George, is to do this, this, and this, and this. The other guy says, wait a minute, Bill, I'm not quite sure that is right. And they have an argument about what it is that this investigation is really all about. And that's very informative. And I think it's not unusual to find people working in a team in an investigation where not everybody has got the same idea of what it is they're trying to do. It can change, too. I was involved in an experiment, well, quite a long time ago, actually, and we ran some sort of design, factorial, fractional factorial, and after I'd done the analysis, I came back and I was a bit crestfallen because nothing seemed to make any difference. None of the things we changed seemed to make any difference. So I came back and I said to these chemical engineers, well, you know, the problem is that none of these factors seem to do anything. One guy looked as pleased as punch. And I said, why are you looking so happy? And he said, well, don't you remember one of those factors that we changed was throughput. We tried, in this pilot plant, we tried doubling the throughput. And nothing changed. That means we don't have to build that new plant over there, because it looks as though if it stands up on the full-scale plant, we'll be able to put twice as much material through this plant. So our objective immediately changed from increasing the yield to increasing the throughput. And, and sometimes you only find that out after you've looked at the data. So you should have in mind the fact when you look at the data, there's more ways of killing a cat than choking it with margarine, is what my father used to say. And so sometimes you look at the data and you realize after you look at the data, you can solve the problem a somewhat different way from the way you originally thought. Another thing I want to emphasize is the importance of the unexpected. Scientific inference is really of two kinds. When you look at that iteration I talked about, the idea and the data, you've got the idea and you're combining that with the data. That's really deduction that you're doing. You're saying, if my idea is right, and this data that I've got, I put that together in my idea, this leads me to deduce the following things. But when the idea, so it's sort of idea plus data that you're looking at there. But there's another aspect which is really like idea minus the data, which is to say, does that idea gel with the data at all? And sometimes the data just doesn't gel with that idea, and so, you know, the data is right. The data's come about by some real process. And so what you thought about that original idea must now not be right, and you must have to modify it and change it. The process of deciding what could have produced that is a process of induction. So it's sometimes the discrepancy between what you would have thought and what the data says that's very important, that is the spark to the tinder of new invention. I was speaking some years ago to a group of, I think, about 400 scientists in Kodak, and I said to them, you know, if you think of all the things you know about film and exposures and cameras and all lenses and all those things, you think of all those things and you imagine them written down in books. Those books that stretch from here to over the Canadian border, we're not trying to substitute for that. We're trying to catalyze that process which employs all that background knowledge that you have. So what we're looking for here is idea-provoking design and analysis. We want to rely on graphics, and the computer can do that beautifully for us. We want to arrange it so that the engineer or the scientist with all his background knowledge in this subject can very readily see what those experiments are saying and can combine it with his background knowledge in this area. You'd like, for example, him to be able to say, let's see what that cube looks like if we look at 3, 5, and 8, for example. Let's look at a normal plot for these particular factors. Let's look at what would happen if we transform one of these variables, things like that. Those are the kinds of things you want to be able to do. So I think we're now ready to summarize some of the things that we've been saying in the tape. We've been saying that we need management to be informed and supportive about these methods. It's not quite like planning a house. You can't say we're going to bring in the roof trusses at such and such a point and the doors are going to be put on at some other time and so on. You can't predict how these investigations are going to go precisely. Sometimes things will be done quite quickly, other times things will take longer. What you can try to do is to use an adaptive strategy which will tend to say that easy problems get solved quickly and harder problems take longer. The analysis should be idea-provoking with pictures and patterns and not numbers. You know, the design should be adaptive so that they match the natural iteration in which natural scientific iteration. And the objective should be carefully chosen. So, statistics is a catalyst for engineering science, not a substitute. The investigator is a detective looking for clues. The induction-deduction process can result in the generation of new ideas. We can't always be right, but we can increase the probability of being right. And then there's the psychological issues, the pressure, the uncertainty under which experimenters have to work, the need for a management philosophy that understands this. So I hope you enjoy your experimentation, and I think we can all draw inspiration from Cole Porter, who said, "Be curious, though interfering friends may frown, get furious at each attempt to hold you down. If this advice you'll only employ, the future can offer you infinite joy and merriment. Experiment and you'll see.